famous image, the so-called pale blue dot image that shows Earth. It's one of the last images taken by Voyager that was sent back, that shows the family group portrait of the sun, which is a very tiny object in the sky at that point, and our planet, Earth, this very, very pale blue dot. And the other planets of the solar system are all in this as well. But what we really do see, maybe in ways that we hadn't anticipated previously. It's not that we didn't intellectually understand this, but when you see an image of it, it changes your perspective. That we are on a tiny, tiny little speck of matter in the universe, and there's this vast, unbelievably expansive universe that exists, and we're just one tiny piece of it. And that there are billions and billions of other stars, and billions, and we are now starting to catalog them as well, planets. And on those planets, there may well be some form of life.
If you look at the Voyager spacecraft, it will probably last longer than the Earth itself. One of the problems we have in being bound to the Earth is the sun stops burning its nuclear fuel in about 4 billion years. It expands out and absorbs the Earth. The Earth will cease to exist. Voyager will not. My name is on the cup that you see in the back of the room, courtesy of Bob Butler. Anton's name is there, so quite literally, we will live longer than the Earth itself.
I was trying to remember exactly when I first met Anton, and I think that there was one point where I went with him and with Bob Butler, who was the systems engineer, out to JPL. We were doing some of the vibration testing on the plasma science instrument on board Voyager, and I think that's the first time that I actually got to meet him. And I was just this, I was this new graduate student who was just kind of following around, trying to learn, what was appropriate to do and what I could do to help. And so they had me, kind of manning some of the testing.
I do remember the plasma team with Professor Bridge and and Anton was part of that, and of course he was the principal engineer on the instrument, and he had to figure out ways that would make the plasma instrument less sensitive to the vibrations that would be coming from our stepper motor.
I don't remember meeting Anton, but he was very important because he could always interface between the scientists and the engineers. And Anton was very good at explaining what needed to be done and how to do it. And later, we worked on various projects, and he was a good person to talk to.
Well, Anton, as you probably know, I call him Anton. I said Anton, but I call him Anton in English. And I don't call him Tony, I call him Anton. He's a very opinionated guy about linguistics. And I had studied some linguistics too, so we had many informed, lively discussions where I had to correct him and he had to correct me about linguistics.
And for almost as long as I have been here, Anton Mavretič has been one of the icons, one of the professors that the students look up to, and that the other professors love to work with. He's a wonderful collegial person and a fun person to work with.
Anton was a leader in transforming what you learned from the science in the textbooks into making sure that you had practical applications associated with it. This lab we find ourselves in is one of the key things that is a legacy of his teaching. He created the electronics program at Boston University.
He called me up and he said, Lenny, you know, I finished teaching the courses for the spring term. I don't have much to do during the summer. Do you have any work at Harvard for me? And I said, sure. You know, I would always find something for Tony to do. He's a very talented guy. And in fact, we had a really good project for him.
Anton Mavretič was crucial to developing instruments to dissect the loss of ozone in the stratosphere. And to do that research required developing new laser techniques coupled to electronics.
You know, the Explorer program was a strikingly significant one for the United States. In 1958, when the first Explorer was launched, the Americans were locked in this struggle, seemingly a death struggle with the Soviet Union. And it was a competition over political and economic structures, pretty fundamentally.
I decided I didn't like that. It was boring. There was they were working on things that I didn't want to get involved with, like bombs.
And the Russians looked to be ahead. When they launched Sputnik on October 4th of 1957, Sputnik 1 is launched, the first Earth satellite. And everybody runs around with their hair on fire saying, oh my gosh, the Russians have this capability the Americans don't have. The Soviets then launched Sputnik 2 that's much larger and carries a dog into space. And that was a big deal as well on the 3rd of November of 1957. The Americans respond by blowing up a spacecraft on the launch pad on December 8th of 1957. So the Soviets are capable of doing two really big, significant space science efforts, and the Americans can't accomplish anything.
Voyager je imel 4 sensorje, bolj komplicirane vektorje je zbiral podatkov energetskih delčkov. Ta je imel pa samo ena kap, one cup. Tako kot je bil Explorer. Ampak razlika med Explorerjem in tem je, kakšno pot ta satelit potuje v Vsemirju. Recimo, Explorer se vrti na pol poti od Meseca in Zemlje in je v tisti orbiti.
So when Explorer is launched on January 31st of 1958, everybody breathes a sigh of relief in the U.S. that we've had this capability and we have demonstrated that we can put something into orbit as well. And that's the beginning point of any activities that you might undertake in space, is getting there. And so there was this opportunity that existed in the 1970s and into the 1980s that would allow a single spacecraft to undertake a flyby of all of those big gas giants. And that's what started the process that led to Voyager. It took a long set of bureaucratic turns. It had to be downsized, upsized, side-sized, and ultimately they were able to launch in the 1970s.
And let me just be philosophical for a minute. 4 billion years ago, this gas cloud condensed, and the sun started burning, and the planets were formed. And 4 billion years later, out pops a little spacecraft that's sending information back to a planet that formed out of the interstellar medium. And this is our first foray back into the interstellar medium from which we condensed. And it is amazing to be alive at this particular moment in time.
Voyager also is getting at this fundamental question, not only how big our universe is and what it looks like, but also in the back of the mind, is there anything else out there? Are we alone? And this is a spacecraft that was going to be shot out into the far distance, as far as anything that human beings could possibly imagine.
The plan for the Voyager spacecraft was always that they would ultimately leave the solar system. But Voyager 1 and Voyager 2 had the capability, which is pretty remarkable, that 40-some years after conceptualization, they could still operate. And the ability to hit what they call the heliopause, the end of the solar system, where the particles that are trapped inside the gravity well of the sun would reach the interstellar medium. That was a remarkable thing, and there's now the interstellar mission that's a part of Voyager that's still operating right up to the present.
We're in the context of we didn't know where the boundary between the solar wind and the interstellar medium was. I've seen papers that said it should have been at 10 AU, not 100 AU. So when we were going out, we kept expecting that we would see it, but it was also possible it would be at 300 AU. And we would never see it. That would be way beyond the lifetime of the spacecraft. So as we were going out, we got closer and closer, and just actually seeing the termination shot gives us an enormous amount of information that we did not have when we started out. So merely getting this far out is a big accomplishment in terms of knowing how the solar system interacts with the local interstellar medium out of which it condensed.
When we launched the spacecraft, we launched Voyager 2 first. You probably knew, not Voyager 1, because it was going to be the second one to Jupiter. Voyager 1 went on a faster trajectory. So Voyager 2 we launched first, and it basically went into a continuous abort on launch, which I presume you've read about. And then people were pulling their hair out, because when it goes to an abort, what does it do? It refuses to accept any external commands. It just goes into safing algorithms, where it's protecting itself. It protects itself from external commands as well as itself.
Clearly, when the spacecraft were first launched, there was media attention at that point. But the real excitement came with the first encounters. First at Jupiter, later on at Saturn, ultimately Uranus and Neptune. And the excitement associated with those was pretty astounding, as we were able to send the two spacecraft within a few thousand kilometers of Jupiter and Saturn, and to get pictures of those planets up close, and especially to get pictures and imagery and data about the various moons. And we learned all of these enormously interesting things about the moons of Jupiter and Saturn especially, and a recognition that they are all in and of themselves distinct, unique worlds that might well, in some cases, harbor life as well.
Voyager, as you know, discovered these volcanoes on Io, the moon of Jupiter, that had 13 active volcanoes when we went by. And of course, the volcanoes were putting out lava, and the lava contained a lot of sulfur dioxide, And that afterwards was picked up and swung through the entire system, and that's how we saw that.
I think the most exciting part of the mission, everyone has their favorite incident, but mine is when we went at Jupiter, very close to its moon Io. We went through the magnetic field lines that connect the Jovian magnetic field to the planet Io. Io turns out to be electrically conducting, and it is generating about a terawatt of power in its motion through the Jovian magnetic field. A terawatt of power is about the output of the US power grid, so this is substantial. There was a lot of uncertainty as to how that was happening. We knew for a long time that that was happening. Voyager gave us the opportunity to go right in the vicinity of Io and see what the mechanism was. And indeed, the plasma science instrument measured the perturbation in the flow around Io that gave evidence for one of the models that had been proposed. Io is a unique satellite in the solar system. It has active volcanoes. That wasn't known until we got there and actually photographed them. It was known that it was a really unique place, and we also were able, with in situ measurements, to determine how the mechanism operated that gets this terawatt of power out of Io.
The possibility of something under the ice sheet on Europa, since we believe that it has a molten core and therefore has heat in the center of that particular moon, and the churning of waves and things of this nature, tidal forces from encounters with Jupiter, and liquid water underneath this ice. Liquid water is the building block of life as we understand it. So if it's there, what might have evolved there? I mean, I would dearly love to see us go to Europa, land on Europa, melt through the ice, and put a hydropod, as they call it, under the ocean to look for sea creatures of some kind. Well, the Voyager spacecraft has a whole series of instruments on it. There obviously were the cameras that were used to take visual images associated with the flybys of the gas giants. Those were the stunning images that made everybody so excited in the 1970s and into the 1980s, and those are no more. In terms of the interstellar mission, we've gone past the point where those can now be used. But there are spectrometers, there are other types of measuring devices that exist on the spacecraft right up to the present, that some of which are still usable, and which are measuring the particles and fields, and especially the radioactivity of the heliopause today.
I need to tell you something about how the solar system formed. It formed out of a vast cloud of dust in the interstellar medium about 4 billion years ago. Gravitational pull collapsed it, and when it got hot enough, nuclear burning started. Once it started burning nuclear energy, it started a wind that pushed back the interstellar medium back far beyond the planets, about 100 times the distance from the sun to the Earth. And that has been the situation for the last 4 billion years.
After so many years of studying the solar wind, we still do not have a complete grasp on how does it come about? Why does the sun evaporate its atmosphere so rapidly? Why does it become so hot? The surface of the sun is about 4,000 Kelvin, the visible surface of the sun. Then you move a little bit further out, what is called the solar corona, and all of a sudden the temperature has jumped up to 1,000,000 degrees. And that's not what anyone would expect. As you expand the gas, you would expect it to cool rather than to unexpectedly heat up. Then, of course, the solar wind becomes really, really fast, supersonic speeds. We are talking about 400 to 800 kilometers every second, not per hour, per second. That's faster than a speeding bullet.
Če se recimo postaviš na sonce in gledaš nazaj na zemljo, so dve krogli, dve krogli. In ti recimo, da je tam žička ali pa ena vrv napeljana od Sonca do Zemlje. In jaz po tej vrvi hodim z eno šalico, pa mi rekel, koliko elektronov, recimo na 10 kvadratnih centimetrov, se je zaletelo v mojo šalico. Jaz se tako nosim na te vrvice. Koliko se jih butne v mojo šalico? Pa se jih bo ogromno zaletelo pri Soncu, ne? In če grem proti Zemlji, če dalje manj. Ampak jaz pa vem, moja šalica je bolj pametna, ona lahko razloči, v katerem energetskem spektru, ki se meri v elektronski volti, ta šalica je narejena, da vzame samo tiste energije, ki so med 10 elektronskih voltov in 7000. Mene samo to polje ne zanima, ta šalica. Jaz z njo hodim, to je pa Faraday cup. Jaz z njo hodim in bo videl, da tole, recimo, je če dalje manj teh energetskih protonov elektronov, ko pridem bližje Zemlje. Če dalje manj, torej to je mi moramo to vedeti.
What Herb Bridge and the group at MIT had wanted to do was to be able to try to measure the solar wind. Now we know now that the solar wind, I mean, this is it blows throughout space. It's always coming off of the sun. It moderates sort of the medium and moderator of space weather that affects all sorts of technological things here on the planet. But you have to think back that before the space age, there was speculation about whether that there really was such a thing as the solar wind. There'd been a lot of speculation, but there hadn't been any experimental proof at that point.
So why does that happen to the solar wind? These are fundamental physics questions that we really do not understand. So heliophysics is concerned, for example, understanding that particular question, or in the case of the Voyager spacecraft, this expanding solar wind ultimately runs into the interstellar medium, where clearly particles come from other stars and galaxies. What is the nature of this interaction? This is very hard to study in a laboratory setting.
When you talk about Faraday cups to most people, they're used in laboratories a lot, and basically they're current monitors. If you have some sort of an accelerator beam, whether you're calibrating instruments, you want to know how much current is actually being provided in that beam, and you literally put a cup in the beam to see how much current is flowing. And properly, what is actually flew on Voyager and was actually developed by the MIT group starting back in the early 1960s is what's really referred to as a modulated grid Faraday cup. The problem was that what Herb Bridge and the group at MIT had wanted to do was to be able to try to measure the solar wind.
Zdaj, naš instrument bo na tisti konzuli, ki je montiran, je gledal, recimo, vsi ti tri senderji so gledali proti Zemlji, tale okrogli, ki ga ti vidiš tam, ta je gledal pa v planete, ki je šel mimo. To je bilo, torej iz teh podatkov, ki nam jih NASA da, kako bo šlo in kako daleč bodo od vsakega planeta, vse je bilo to nam znano, to so že oni nam dali podatke. So se potem konstantno korigirali, leto dve se stvari spreminjajo, so fiziki pletijo v laboratorijih, meni da bomo pa to spremeniti, pa on spremeniti, pa tretje spremeniti, da bomo optimizacija. Nikdar ne moš ti reči, zdaj pa tole naredi, pa bo fertik. To ne gre.
PLS is a marvel of design in the sense that it functions perfectly. that it has functioned perfectly since the early 1970s. I mean, it was launched in 1977. They had some ideas for this in the 50s. They got the first contract in 69. They started building these, the prototype and the two flight models, testing them, perfecting them. And you think of the extremes of space. They couldn't exceed the space footprint that they were allowed. They couldn't exceed the weight limits. They had to work within very extreme constraints.
Our instrument goes from being fully in the sun and even more fully near the Earth, and the Earth is very hot, it's room temperature, that's hot in space, to way away where there's no energy source at all, so it runs very cold. It wants to run at, say, 4 degrees Kelvin, or 10 degrees Kelvin, just above absolute zero. So how do you design the instruments to survive such a huge temperature range?
I think throughout MIT's history, the students, the faculty, the researchers trained here have had an obsession with beautiful design. Not just in the obvious ways that we're one of the first schools of architecture or that drawing and drafting were key skills, but visual knowledge is fundamental to a scientist's and an engineer's education. And being able to build an instrument that works perfectly, that functions exactly as designed and planned, that allows you to conduct an experiment and be confident in the results that you gain, that's an obsession.
Bruno Rossi was a famous Italian physicist who was very interested in cosmic rays. He was at the Los Alamos project during the war, as was Herb Bridge, as was any other person who knew anything about physics, because they were all drafted into either the radar project at MIT or the bomb project at Los Alamos. After the war, Bruno Rossi was offered a chaired professorship here at MIT to do cosmic ray research. He came back and he brought Herb Bridge. Bridge eventually got a PhD. The space age started, and Rossi was very interested in getting into measuring cosmic rays above the atmosphere.
Ko sem prišel na intervju tukaj na MIT, na dan, tisti dan, ko sem prišel, smo imeli sestanek prav o načrtovanju Explorer missions. In jaz nisem niti vedel, kako bo ta intervju izgledal, ampak smo bili v pisarni, okrog mize je bil ta profesor Bridge in še drugi.
In the area of aerospace, MIT was a pioneer. It was the first university in the United States to offer a graduate degree in aeronautical engineering back in 1914. So already people here had been experimenting with flight, with structures, with instrumentation, weather, meteorology, all aspects of operating in the Earth's atmosphere, if you will.
Na tabli so začeli risati fiziki, kaj hočejo. Ne? Oni so iskali glavnega inženirja, ali pa tukaj se imenuje project engineer, ki bi potem to speljal njihove ideje, kar hočejo narediti. Je bilo na intervjuju veliko drugih fantov. Jaz sem pravzaprav zelo, rekel sem, mislil se to, kaj se bo mene ne bodo najeli, jaz te čas zapravljam. V glavnem sem se ponižno počutil, ker je bil že takrat za mene MIT maskej. V glavnem sestanek je laufal, približno 3 ure, in profesor Bridge je pričakoval, da sem jaz vključil v to debato o načrtovanju tega. In jaz sem se seveda vključil in sem tudi veliko Američan svojih 5 centov tudi zraven dal. Tako da verjetno jim je bilo všeč. prav gotovo, ker sem po čez nekaj dni dobil telefonski klic od profesor Bridgea, da me bo sprejel v službo na MIT.
I'm sure if you asked the scientists involved in the coronagraph, they would say there's a practical aspect to it. And one can say, well, if one understands the physics of the sun, you can understand how the solar storms, for example, and flares can affect communications back on the Earth. But it was primarily a fundamental physics research.
Je bilo instrument narejen za raketo in ko je raketa šla gor do recimo 100 km visoko, 110 in ko je šla pa dol. In ko je prišla na vrh, na tako zvani apogee, so se odprla padala in naš instrument je dol letel s padalom in 100 km dol na tla. Ta instrument je bil tako narejen, da je bil voden na ta način, da je vedno instrument gledal v sonce. Ko je bil na vrhu in skozi dol je vedno gledal, vedno je sledil sonce, vedno. Ampak je tudi tam ena elektronska naprava na tem, da je zasenčil sonce, da smo lahko gledali čistale rob od sonca ven.
The instruments that we design are very complex, mechanically, electrically, optically, and we needed people of Anton's caliber to work on. I remember when he first started here, for one of our instruments, we needed a copper vapor laser. Nobody commercially built a copper vapor laser, so we designed and built one in-house. And one of the necessary components for that is a high voltage power supply that powers this laser. Very difficult design problem, and we weren't very successful at it until we got help from Anton and from eventually his grad student Joe Demuse, who ended up working here full time.
Ker sem se že Matija na koronograf delati, od tam se jaz potem pustil in sem šel za profesora na Bostonsko univerzo. In ko sem bil na Bostonski univerzi, sem delal s profesor Aldersonom.
At the time he was working at Boston University, and there was a tremendous need for expertise in how flight space systems are designed and what the cutting edge of engineering technology was. And there are very, very few of those experts, and Dr. Mavretič was one of them, and so we immediately became associated with him and his work and the students that he brought.
At the time, ozone depletion was a big problem. People had discovered the ozone hole over in the Antarctic, and there was more evidence of that happening, and I felt that it had much more relevance to society, which is, I think, one of the big reasons I transferred.
The understanding of the potential threat for destroying ozone, and of course ozone is important because it protects all living species from ultraviolet radiation at the surface, and the amount of ozone that's in the stratosphere is a tiny amount. If I compressed it down to this table, it would only be 1/8 of an inch thick, so a tiny amount of ozone, but it's singularly important for protecting DNA in living species from being broken by ultraviolet radiation. And it's the only molecule in the atmosphere that can do this. So it's a very crucial part of nature's system for protecting life at the surface.
What's special about Professor Mavretič is that when he's explaining these things to you, there's both an adoration of the subject. He clearly loves the subject, but also a deep regard for the person he's talking with. So this is rare among professors. Many times professors are self-absorbed.
Anton was one of the people who introduced me to Boston University. He helped me meet the other faculty, and he helped me understand the students. And as I was learning to teach, he was a mentor in that aspect.
I was privileged to get to know Professor Mavretič through a series of Center for Space Physics projects that he worked on here, usually in collaboration with Professor Fritz. Sometimes he helped us with Professor Chakrabarty. One particular project in which I participated, we flew a mirror that I had made in a rocket to try to image planets, and I remember Professor Mavretič being very helpful to us in trying to plan that mission.
Space physics covers so many areas. It covers mechanical engineering, from the building of the structures and the propulsion. It covers all the instrumentation, that's our department, electrical engineering and computer engineering. It covers the science. What do you build the instruments for? And that involves astronomy, physics. And so all of these departments come together in a center for space physics.
He comes at space sciences from an engineering perspective. A scientist might say, I want to study what happens in the universe, how the cosmos work, how astrophysical plasmas work. And somebody like Anton takes that scientific query and turns it into an engineering problem to solve.
Space physics is a small part of a large operation, but in addition to his work for space science, Professor Mavretič is well known for his work in helping students understand the importance of analog electronics. It's a lost art, analog electronics, but it is still vitally important to the way engineers do their work.
The planet Earth is surrounded in a magnetic bubble. Basically, the Earth itself is a dipole magnet. And this magnetic property of the Earth is, in fact, one of the very reasons that life exists here at all. Because the plasmas operate such that they deflect harmful particles from the sun around the Earth. And so understanding how this environment, this extended magnetic environment of the Earth operates is fundamental to understanding how habitable environments arise in the universe. So the type of research that Anton is involved with involves putting these sensors out directly in the region where this magnetic field effect is strongest. So there are these highly energetic particles that are trapped in this magnetic field. And we want to understand where they come from, what governs their density, and how they're lost, the processes that causes them to be lost. And these are called the Van Allen belts, which is a term that many people know.
Wind is a satellite that is still functioning. It was launched in 1994, but it's still in orbit and fully functional.
Wind ima veliko potovalno pot v bližini Zemlje je bila malo drugačna kot drugih satelitov, ne?
It is at the Sun-Earth first Lagrange point, which is 4 times further away from the Earth than the Moon toward the Sun. It's a very unique location in space where the pull of the Sun, the gravitational pull of the Sun and of Earth are equal.
Zdaj pa, če so sončne pege na Soncu in so izbruhi malo hujši na enem delu Sonca drugim in ta solarni veter, te delčki, ki letijo iz Sonca proti Zemlji, včasih zavalovijo. Tako kot si recimo lahko zamislimo dež, ko pada in veter zapiha in tisti dežnik včasih dosti ne pomaga. Zato, ker bi rekel, vektor ali pa pot, ki je bila nakazana kapljice, se spremeni. In to se isto dogaja tudi v vsemirju, da vsi tole bombardiranje iz Sonca ne gre po eni ravni črtici, pa kar pade v magnetno polje. In če priti v magnetno polje pravokotno nasilnico, se zavrti okrog in tam ostane. Če pa pade recimo pod enim kotom, recimo 7 stopinj, pod enim kotom, vektorjem preleti, potem se pa ta energetski delček vrti okrog magnetne silnice in pade ali na južni pol, ali pa na severni pol. In ko ta delček preleti na tisti del dežnika, ki ima sosipijo skupaj, in tisti delček zgori, in to se imenuje aurora borealis.
If we understand the flow of solar wind, and if we can actually understand it to the point that I can predict it like Earth's weather, I can, let's say, look at the sun and say that, oh, there is a storm happening, therefore, 3 days from today or 2.5 days from today, there will be a major event, we need to do something. And power grid operators can actually protect themselves against these sort of things. Then that would be really practical. We are not quite there yet. Our understanding is not as good that we can predict it in 2.5 days. Right now, the best we can do with high reliability is to put a satellite at this magical first Lagrange point, where it measures the solar wind, and I know that whatever hit that satellite, half an hour later it will hit Earth.
So when an electron interacts with oxygen, for instance, I get a red color, or perhaps a green color. There's this particular type of optical spectrum, it's almost like a fingerprint that tells me exactly what particles were hit. So if I look for that fingerprint in an extrasolar planet, maybe I can use that signal to discover life. So this is sort of a direct connection between the fields that we call space physics and astrophysics.
The Faraday cup, in spite of its age, the Faraday cup, unlike modern instrumentations, and we have other types of instrument that can measure solar wind, thermoplasma, the protons coming from the sun, the Faraday cup has a very unique characteristic, that it is, by the nature of its very simplistic design, it can operate through solar energetic particle storms. The sun, when it belches out one of these big coronal mass ejections, it's not just the faster solar wind that comes, but high energy particles come with it. These high energy particles, while we are trying not to measure them, modern instruments tend to be knocked off by them. But the Faraday cup is a very, very robust instrument that it can operate right through happily these events, completely oblivious of the energetic particle environment, and therefore it's an ideal sensor for this kind of space weather forecasting, because they operate through the worst of the weathers, not just good weather conditions.
The more we learn about the sun, the more we understand what is taking place that will affect us, and the more we understand the universe as a whole. So there is always solar science that's associated with virtually every human spaceflight mission in orbit. The International Space Station that's currently in orbit, the Skylab program of an earlier era, the Soviet programs with Mir and the Salyuts, all had solar observatories on them to see what was taking place, to try to understand the sun more effectively. And we've continued to do that up to the present.
And this is where we live, on a blue dot.
In order to better understand our own environment, the space environment around our planet, what we need is to come up with ways not to deploy a single instrument into space, but rather to deploy networks of instruments into space.
Recimo signali, ki prihajajo iz Voyagerja sedaj, so strašansko obremenjeni z šumom. In zdaj pa rečemo, kaj je šum. Šum v elektriki je, ko vsi materijali imajo šum. Torej, šum se da izmeriti statistično se da zmeriti v voltih, tako ga mi merimo, ne. Ampak šum je proporcionalen kvadratnemu korenu iz temperature. Pa noter je še bandwidth in druge stvari so noter. Ampak v bistvu šum je proporcionalen kvadratnemu korenu temperature.
So rather than, for instance, deploy one particle detector of the type that Anton develops, why not 10? Why not 10,000?
Čim višja temperatura, več bo šuma. Ampak recimo moraš šum, recimo, če je šum 4-krat večji, bo napetost šuma šla 2-krat gor, nekaj kvadratni koren. Se pravi, da če je instrument zelo topel in vroč, bo imel več šuma. Ampak zdaj recimo, to je to. Če gremo pa na nižje temperature, je šum je manjši in manjši in seveda pri nič stopinj Kelvina šuma ni, ker se vsi elektroni stavijo in se ne vrtijo več okrog svojih osi, vse se nekako umre.
And this is where we live, on a blue dot.
The problem with one sensor is the same as the problem with a man with one watch versus 2 watches, right? If you have one watch, you know what time it is. If you have 2 watches, you have no idea what time it is. If you have 10 watches, you begin again to know what time it is because you can take kind of the average of them all, right?
Če pa mi pošljemo signal po žici, ki se bliža tisti napetosti fundamentalni šumu, je pa lahko signal tako velik kot šum in končno je šum pri določeni večji, kot je pa signal. To je ta del, ki rečeš, aha, zdaj pa premalo elektronov potuje po tej žici, maršira jih zelo malo in jih je šum prevzel. Se pravi, temperatura tistih elektronov, ki frčijo po žici, jih je več in oni so bolj močni in je šum večji. Ampak njih oni ne zanimajo, nas zanimajo informacije, ki so v tistem toku, ki smo ga mi poslali.
So this is the idea behind sensor networks. If we can deploy sensors all over the magnetospheric environment, then we can begin to build a picture of how this object varies in space, time, energy, wavelength, all the dimensions of variability that it embodies.
4, 3, 2, 1. We have ignition and we have liftoff.
The Titan Centaur rocket carrying the Voyager spacecraft lifted off perfectly into a hazy blue sky. The solid rockets doing the initial job, then the old Titan and the Centaur igniting for the final boost into orbit. An hour later, the Centaur rocket ignited again, blasting Voyager out of this world into an escape trajectory. A second Voyager in the $300 million program is due to be launched 12 days from now. Nearly 2 years from now, the Voyagers will arrive at Jupiter, and we'll begin to find out if it all was worthwhile. This is Jules Bergman, ABC News at Cape Canaveral.
Domotožje, to je naravni del. Če si doma, recimo iz kakšne vasi v Ljubljano, recimo iz Boldraža, pa priješ v Ljubljano kot otrok, ti je lepo, si nesrečen, ker nisi na Boldražu. Če si na Boldražu, dolg časa si nesrečen, ker nisi v Ljubljani. To si svetovni vagabond je hitro. Jaz sem bil, moj tosic mi je rekel, ti boš postal vagabond. Boš nesrečen, ko si v Ameriki, zato ker nisi doma. Ko boš doma, boš nesrečen, ker nisi v Ameriki. Rekel, to so dileme, ki te bodo držale celo življenje.
Ja, moj brat je zapustil to dedovo domačijo, Mavretičevo, 57. leta, ko šel v Ameriko. Vsem nam je bilo hudo. šel je z ladjo Hrvatska po imenu in je bila oddaja, še pomne, kako je bila naslov, kje so naše ladje jugoslovanske. In to smo ob torkih obvezno poslušali, kje je ladja Hrvatska, ker je plula to 3 tedne, kje so se ustavili, kje je bil, ne. Tako da smo skozi to sledili, to pot, kako je potoval v Ameriko.
Ljubica